Hello, Thav, can you see my screen? Okay. So we'll start by 6-5. No, I just said that we will start by 6-5. Okay. Okay, so uh, today we'll discuss about problems related with the week 6 lectures. So in the week 6 lecture, the dislocation characteristics have been taught, and the stress field around the dislocation and the uh, interaction between dislocation or partial, means dissociation of dislocation into partial. So uh, first question we'll solve. So have you gone through the lectures for week 6? Okay. Okay, so means dislocation you know about little bit. In the week 5 lecture also dislocations was discussed. Okay, so I just give a brief review. So we know that there are two types of dislocation: screw dislocation and edge dislocation. So we have Berger vector and line vector for both. So for the screw dislocation, the Berger vector is parallel to line vector of the dislocation, and for edge dislocation, the Berger vector is perpendicular to uh, line direction, line of the dislocation. So if we talk, let's say, so what are the dislocation properties for these two type of dislocation? So if we talk relation between dislocation line and Berger vector, so for screw dislocation it is parallel and for edge dislocation it is perpendicular. Next, what is the direction of step created while dislocation leaves the crystal? Means when the dislocation move through the crystal and exit. So what is this? Means some step is created after. it leaves the uh, crystal. This so this the amount of this step is generally given by Berger vector. So it is equal to the Berger vector. So what is so the direction of this step is also depends on the two types of screw dislocation. So for screw, yeah. So for screw dislocation, it is the step is parallel to Berger vector movement, and for edge dislocation, it is also parallel to Berger vector movement because it is uh, in the path of the Berger vector only. Next, the direction of dislocation line movement. Direction of dislocation line movement means when the dislocation both screw and edge dislocation glide, so the line dislocation line also move. So what is the direction of dislocation line movement respective to the Berger vector? So for the edge for the screw dislocation, it is perpendicular to Berger vector means line movement, and for screw dislocation, it is sorry for edge dislocation, it is parallel to Berger vector. This line also move as the Berger vector moves in the same direction. And process by which dislocation may leaves a slip plane, leave slip plane. So for screw dislocation have means uh, the Berger vector and line vector are both parallel. So the screw dislocation can move towards any plane which is uh, coming to its path. So uh, that slipping on another plane from the primary dislocation gliding plane, for screw dislocation it is called cross slip. So when it's change its gliding plane, so it uses cross slip means from one plane, this is another plane. So when it is moving on this plane and uh, change this its path from to this plane, so this is called cross slip. And for edge dislocation, the dislocation leave the slip plane by climb. So climb is what means it can be positive or negative. Positive means upward, and negative means down downward. So how can we say that it is upward or downward? So we know that the dislocation is half the plane. Yeah. So this half plane, if we remove a atom from this, so the extra half plane will climb to in upward direction. So when we remove atom, so the climb will be upward, and if we add atom below this point, so this point if we add, so the motion of the climb is downward. So this is called the downward climb. So negative climb. And one more thing regarding the dislocation motion, that the screw dislocation motion is conservative, and edge dislocation is non-conservative. Conservative, non-conservative means in during cross slip, the volume is constant, but in the non-conservative, volume is not constant, because when we remove or add atom, so very slight change in volume happens. So the climb results in volume change. So it is non-conservative, and the screw dislocation motion is conservative. And so further, the energy of the dislocation means if this extra half plane is there, so at the upper side the atoms are squeezed, and at the they have half of this below side, it they are stretched. So because of the squeezing and stretching of these atoms, some stress generates around the dislocation extra half plane, and at this core also, means this extra half plane is known as the core. And so this stress value also changes from the dislocation core to uh, to the distance, to a certain distance from this dislocation core. So there for a screw dislocation, if we derive uh, a stress field, so for the screw dislocation, there are only four components of stress acting on the screw dislocation. So it is xz 0 0, sigma yz, and here zx, sigma zy, and 0. So in the screw dislocation, the stress component uh, have only four components, means, and the all, total means all four are shear forces. But for edge dislocation, the stress field is given by sigma xx, sigma xy 0, sigma yx, sigma yy 0, and both are 0, and here sigma zz. So here normal and shear both components are there, because in climbing some normal forces relate which results in volume change is also required. So for edge dislocation, there are both type of components, normal and shear stress. So relating to the this stress field around the dislocation, the some energy is also stored uh, around the dislocation. So the energy is given by alpha GB square. You can see the derivation in the lecture videos. So alpha is some constant. Yeah, we can write it for edge dislocation. It is GB by 1 minus nu ln of r by r small r. So r is the dislocation core radius, and r is the distance from core. So this for H dislocation it is given by this. So G is the shear modulus, B is a Berger vector, and nu is the Poisson's ratio. While if we write the sorry, yeah. So for screw dislocation, the energy stored around dislocation core is given by GB by, yeah, only GB ln r by r. So if we add these two, so this term comes. So yeah, so the total energy will be E H plus E screw plus E core. I mean dislocation core has having some elastic energy region. So that this term gives E equals to alpha alpha GB square. Yeah, here also it is square. And the dislocation lines which represents like you will see in that one team micrograph is shown in the lecture video, so that have curved dislocation lines in a sample TM sample preparation. So the curved dislocations line show that they are the mixed dislocation, means they have both components edge and screw at other region, means at different region of from the uh, crystal lattice. So edge and screw both characters mixed dislocation have. So for this dislocation, so you where you are seeing that they are ending in the sample, but it is not the real case. The either they are making a loop or they are ending at a free surface. So the dislocations end points are free surface, green boundaries, phase boundaries, and loop, means they are making loop, so ending at themselves only. So next point is that The dislocation line also consists some line tension. Means if they are curved, straight dislocation will not have any line tension, but they are if they are curved, so they will have some line tension. So that line tension formula is given as alpha GB by R. So the alpha is the same constant in the energy, G is the shear modulus, B is Berger vector, and R is the dislocation core radius. So here alpha value is generally given by zero point 0.5, or in if any problem is given, so the alpha value is also provided in that. Next is the means the dislocation having some Berger vector. They try to minimize their energy by dissociating into partial. So if one dislocation have a Berger vector B1, so it can dissociate into two partial having Berger vectors B2 and B3. So how the dissociation happens means if the energy of the dislocation is reducing in dissociation, so only in that case the dissociation happens. So if we calculate the energy for this, so alpha GB square should be greater than alpha GB B2 square plus alpha GB3 square. So if we take it common, so B1 square is should be greater than B2 square plus B3 square. Then only the dissociation of the dislocation happens. So this is the energetically favorable condition for dissociation. Okay, so we'll now solve the problems. So in this question, so we have asked that consider the reaction of two parallel dislocations of Berger vectors B1 A by 2 110 and B2 A 0 bar 1 1. What would be the Burgers vector of the product dislocation if they react with each other? Would the reaction be energetically favorable? Yeah, so I one more point I missed. Like two dislocation can also react to form a final Berger vector if only the it is energetically favorable. So if the energy is reducing by reacting to dislocation, so only in that condition they will add. Otherwise, they will not add and repel. So the what so if they react with each other, so the final means B3 will be B1 plus B2. So if we calculate, B1 is A by 2 110 plus A0 by 1 1. So we will just do the simple addition. So the B3 will be A by 2 plus 0, then A by 2 minus A plus 1. So not plus, this is 0 plus A. So this can be written as a by 2 minus a by 2 and a. So if we take a by 2 common, so this will give a by 2, 1 bar 1 and 2. So B3 Berger vector is given by this a by 2, 1 bar 1, 2. And would the reaction be energetically favorable? So we will first take the square in addition. So B3, if we take B3 square will be a square by 4, 1 square plus 1 square plus 4, so 2 square. So this will be uh, 6 by 4 and 3 by 2. So this will be 1.5 a square. And if we take b1 and b2, so b1 square plus b2 square will be a square by 4, 1 square plus 1 square plus a square by 4, 1 square plus 0. So this will be a square by 2 a square by 2. So this will be a square. So the energy before reaction is less than the after addition. So this reaction is not energetically favorable. Next problem is similar to this. So when an A by 2 bar 110 dissociates into two partial dislocations A by 6, this, and on what 111 plane must the partial dislocation lie? So if two dislocation partials means if one dislocation is dissociating into dislocations partial, so on what plane it will dissociate? So the plane for the dislocation partial can be obtained by the cross product of these two Berger vectors. So if we take cross product, so this will be I j k minus 2 1 1 and minus 1 minus 2 and minus 1. So this will give minus 1 plus 2. This will be, so this will give 2 bar 1 minus 3 I minus 3j and minus 3 k. So the Miller indices for this will be 111. So this will be the dissociation plane for these dislocation partials. Or one more thing, like we can cross check also if it is lying on this plane only. So by how to cross check? So by dot product, if we do 2 bar 1 1 and 1 so this will be minus 2 plus 1 plus 1. So this will be 0. So the dot product of the dislocation partial and the dislocation plane will be 0. So we can say that the 111 plane is the plane, partial plane for the dislocation, partial dislocations. Next question we have asked that into what other pair of A by 6 211 partials could the A by 2 dislocation in example previous problem dissociate? On what plane would they lie? So this a by 2 bar 1 1 0 can dissociate into the other partial a by 6 bar 2 1 bar 1 plus a by 6 bar 1 2 1. So these two partials are different from the previous partials. This a by 6 2 bar 1 bar 2 1 1, a by 6 bar 1 bar 2 bar 1. So these are different. So the generally this dislocation partial we are uh, dissociating from this dislocation vector is energetically favorable. So you can cross check it by the energy addition formula. And yeah, so partial could so these are the another two partials for this dislocation. And on what plane would they lie? So we can say that by if we do cross product for this, minus 2 1 minus 1 minus 1 2 1, so that will give I 3I plus 3J minus 3K. So 3 will be give 1 1 minus 1. So this is the plane on which they lie. This is the second type of partials are lying on this plane. So we can check it by cross checking also. So the minus 2 plus 1 and plus 1, this will be 0. So next plane we have asked that on which 1 1 0 planes of BCC iron can a dislocation with the Berger vector a by 2 1 1 bar 1 move. So this is also same related to the previous. So we have to check whether the dot product of this Berger vector and plane is 0 or not. So first we will check for the 1 1 0 only. So 1 1 bar 1 into 1 1 0. So this is we can see no, first 1 1 0 will not give 0. So if we take 1 bar 1 0 plane, so this will be 1 minus 1 plus 0 will be 0. So the 1 minus 1 0 plane uh, is the uh, means the plane of BCC iron can a dislocation with so the dislocation will glide. So one more thing, it we can say it gliding plane or slip plane. So the slip plane for this dislocation is the 1 minus 1 0. Next question we have asked to do energy calculation. Like consider the reaction between parallel dislocations given here. In each case, write the Burgess vector of the product dislocation and determine whether the reaction is energetically favorable. So if we for first equation we have to write Burgess vector. So a by 2 is common. So a by 2, this will be 1 and 1 2 minus 1 1 0, and this will be 0 0. So we can write it as a 1 0 0. And for this second, this is a by 2 1 and 0 is 1, 0 and 1 is 1 and 1 1 0. So a by 2 1 1 0 is the Berger vector for the B. For C, this will be a by 2 1 and 2 minus 1 0 minus bar 1 and the 0 1 is 1. So this is the dislocation Berger vector for the C reaction. So we can now calculate the energies for A. This will be A square by 4 1 plus 1 plus 0 plus A square by 4 1 plus 1 plus 0, that will be, if it A square 1 plus 0 plus 0. So if we take A square by 2 A square by 2, so that will be A square equals to A square. So means the energy is equal for both before reaction or after reaction. So this case is also feasible, energetically favorable, because the energy is not increasing after reaction. Favorable. For the B option, this is A square by 4 1 plus 0 plus 1 plus A square by 4 0 plus 1 plus 1. So is it equal to this? A by A square by 4 1 plus 1 plus 0. So this will give A square by 2 A square by 2. So this will be A square, and it is here A square by 2. So energy is reducing after the reaction. So it is also favorable. For the C option, it is A square by 4 1 plus 1 plus 0 plus A square by 4 1 plus 0 plus 1 equal to A square by 4 2 square plus 1 square plus 1. This will give, this is 0. This will be A square, and here it will be A square by 4 into 6. So it will be 1.5 A square. So the energy increased after the reaction. So it is not favorable. Okay, so we will discuss some assignment questions also. So these assignment questions are from the previous year. So we have asked that dislocation can terminate it. Are they terminated phase boundary, green boundary, free surface, or inside green? So can you tell which option is correct? Okay, you are asking, ma'am, does the BCC iron part have any significance, or it is just extra data? No, it's just the question. Means for BCC and FCC, the slip plane are different. Like for FCC, we generally use 111 plane, but for BCC, 110 planes are the favorable planes for the dislocation moment. Okay. Yeah. First three option correct. Phase boundary, green boundary, and free surface. Second question is that which of the following statements are true regarding edge dislocation? So, like direction of dislocation line movement is perpendicular to its Berger vector, or they are parallel to Berger vector. Dislocation leaves the slip plane by the process of climb, or dislocation line is perpendicular to Berger vector. So we have discussed the dislocation characteristics. The question is readable, or should I increase the font? So for the edge dislocation, which option is correct? Okay, so we in the dislocation characteristics, uh, I told that for edge dislocation, the Berger vector and line vector is perpendicular, and for screw dislocation, the both are parallel. And so also we have discussed that the line movement is perpendicular, parallel to Berger vector. Movement is parallel to Berger vector, and here as for this, the movement is perpendicular to Berger vector. Same for edge dislocation, the dislocation leave by climb, and for this a cross slip. And yeah, and dislocation line movement for the Berger vector, yeah, is parallel, and for school dislocation it is. So now can you answer option one and three? Yes. Yeah, one more. The dislocation line is perpendicular, means no. This is second question. Now, so the correct option for this is B, C, and D. The dislocation line is perpendicular. We have some mistake. Means the here it is written line movement. So line movement is parallel, and dislocation line is perpendicular. And so we have for the edge dislocation, the line movement is parallel, and the means this is the extra half plane. So this is the Berger vector, and this is the line. So dislocation line is perpendicular, but it moves along the Berger vector only. As dislocation move in this direction, so the dislocation line also move parallel to B. So the B, C, and D option is correct. Okay. So we'll go to next question. So we have asked that which of the following statement are true for edge and screw dislocation. Yeah, I have to tell one more thing. The Berger vector magnitude for dislocation is fixed. Means until it dissociates. Means the before dissociation, the Berger vector will not change at any point in the dislocation line. So Berger vector will always be constant. And second thing that the both edge and screw dislocation on its primary plane uh, can move by glide only if they change the plane. So the edge dislocation uses climb to change the slip plane, and the screw dislocation uses cross slip to change its plane. So from these option, first option says that in edge and screw dislocation, the budget vector is continuously changing across the dislocation line. So this option is incorrect. Means the budget vector is constant across the dislocation line. Second option says that in screw dislocation, the budget vector is parallel to dislocation line. So this is correct. Both edge and screw dislocation can move by glide, so this is correct. And screw dislocation can move by glide as well as cross slip. So the last three options are correct. Okay. So next question is that sorry, a glide loop is shown in the figure below with the Berger vector lying in the plane of paper. Which of the following statement are correct? So the line vector is along this. So you have to tell at which point the line vector will be parallel or at which point the line vector will be perpendicular to Berger vector. Parallel it A and C. Yeah. So if here the parallel line vector to Berger vector will give screw component, and B and D it is perpendicular. So that will give edge component. So the dislocation in point A and C are of screw nature, and yeah, so A and C it is T, and here it is downward and upward or perpendicular to B, and the dislocation in points B and D are of edge nature. So we move to next question. The elastic strain energy associated with dislocation 1 is 2 times that of dislocation 2. Which of the following statement can be independently true. So we have given that E1 is equals to twice of E2. So energy for dislocation is given by alpha GB square. So we can uh, find the relation between Berger vector by this relation. So can you tell which option is correct? Option 3, yes. And one more option is correct here. We have, let's see, yeah. So B1 equals to root 2 of B2. So one more thing, like for H, we have asked that H and screw dislocation. So for H, it is GB square 1 minus nu ln R by small r, and for screw, it is GB square by no on 1 ln R by small r. So if we put Poisson's ratio 0.5, so that will give GB square. Here if we take zero point 0.5, so 1 minus zero point 0.5 will give zero point 0.5, and on the up, upper side we will take 2 ln of r by r naught. So we can write that E edge equals to twice of E screw if the Poisson's ratio is zero point 0.5. So we can say the dislocation 1 is in edge dislocation and 2 is the screw dislocation. So B and C is correct answer. Next, uh, yeah, option 3 is correct and 2 is also correct for the fifth question. Yes. So moving to the sixth question. While comparing pure screw and pure edge dislocation, elastic strain energy per unit length of dislocation and line tension are higher for, uh, is it higher for screw dislocation or edge dislocation? Just now we have discussed that in the means the Poisson's ratio in the denominator will give higher terms for edge dislocation every time. So the energy for edge dislocation is generally higher as compared to the screw dislocation, and the line tension is also generally higher for the edge dislocation. So the B option is correct, means the energy and line tension are higher for edge dislocation. Next question we will move. So we have asked for a BCC material, select the possible slip plane for screw dislocation having Berger vector A by 2 1 1 1. So we have how can we find the slip plane for a Berger vector? Dot product is 0. Yeah. So can you tell which option is correct? Option 2 and 3, yes. Means 1 0 minus 1 and minus 1 1 0 is correct. B and C. Next question will move. Which of the following statements are correct? Either so first option says dislocation tends to have smallest Berger vector as possible. Dislocation may dissociate into partial to reduce energy. There is a line tension associated with the dislocation, and multiple dislocation can associate to form a single dislocation. So in this means all options are saying a correct thing. Is the dislocation tend to have smallest Berger vector. So if it have smaller Berger vector, so the energy will be less. So the first option is correct, second option is correct. There is a line tension associated with the dislocation, and the multiple dislocations can associate to form a single dislocation. Means if they are reducing the energy. Option 2, 3, and 4. First option is also correct. Okay. So moving to next question. Mark the correct statements regarding the motion of dislocations. Hmm. Done. Okay. Option 4 is incorrect. Yes. So yeah, for this A, B, and C are correct. Means if we so the dislocation only move if so the dislocation motion is generally done by if we apply some stress. So the shear stress uh, generally helps in the movement of dislocation or glide. So if screw dislocation of opposite sign glide in opposite direction for a given shear stress. Edge dislocation has uniquely defined glide plane. Means for edge dislocation, only one glide plane is uh, primary glide plane is only one. But for screw dislocation, there can be infinite planes. And for a given shear stress, slip direction is independent of nature of dislocation. Means if uh, we have provided a shear stress, so slip direction will be in the shear stress direction only, independent of the nature of dislocation. Means either it is positive, negative, edge or screw. Means if shear stress is applying in some direction, so the dislocation motion will only happen in that direction. So A, B, and C option is correct. Just 1 second. Okay. Sorry for the interruption. Uh, so, next question we have asked that determine the elastic strain energy of a screw dislocation in copper. It is given that magnitude of Berger vector and shear modulus are 0.25 nanometer and 48.3 GPa respectively, and the multiplication factor is zero point 0.5. So we know that the energy for screw dislocation is written as alpha. If we write a common term, so the alpha is zero point 0.5, G is 48.3 into 10 raised to power 9 multiplied by this Berger vector. So Berger vector is 0.25 into 10 raised to power minus 9 square. So this will give 1.5 into 10 raised to power minus 9 joule per meter. So the third option is correct for this. So we'll discuss some more questions. Yeah. Okay. Yeah. So during conservative glide of a dislocation in a single crystal, which statements about the Berger vector are correct? Conservative glide we have discussed in the characteristic. Means conservative will give volume, means volume is constant, and in non-conservative the volume change. So for a single crystal, if a conservative glide is happening, so and, first thing is that the Berger vector for a single crystal means in a single crystal all atoms are arranged in a sequence. So the only uh, Berger vector will be equal to lattice translation. Means from one atom to another atom, and the Berger vector is in the in the week 5 lecture we discussed the how can we find the Berger vector by uh, forming a a Berger circuit around a dislocation. So it is defined using a Berger vector. Its magnitude changes during motion. No, the Berger vector magnitude does not change, so it is wrong. First and second option is correct. And fourth is it represents only the direction of lattice distortion. Yes, so third option is also correct. Means the step creating after the uh, glide. So that will means there are several planes. So the one plane, the direction of lattice distortion will be this. So the budget vector also represents the lattice distortion direction. So the first and the 1, 2, and fourth option is correct. So second question, porous for a straight edge dislocation in a linear elastic solid, the strain field around the dislocation contains. So for a straight dislocation, which stress components we have? I mean normal stress component or sorry normal strain or normal stress component. Sorry, not normal and shear. Option 3, both shear and normal strains. Yes. Yes, so both shear and normal strains for edge dislocation comes. Yes, it can be written as with the stress component sigma or E. So this will be 0 and sigma xx, sigma xy, sigma yx, sorry, epsilon yy, and epsilon zz. So the normal and the shear component both we have. Next question. Which of these stress components of screw dislocation has radial symmetry? So the x, y, and z uh, coordinate uh, tells about a stress component in that direction or plane, but the radial direction shows the symmetry. Means the theta z is the radial component. So it shows the radial symmetry around the dislocation core. So the sigma theta z represents the screw dislocation radial symmetry. Fourth question is edge dislocation does not have this stress component. So just now we have made the matrix, means which stress components are missing. Sigma xz, sigma yz, and sigma zyzx. So here only this C option is correct. Means sigma yz is missing in edge distribution. So we have asked that for a straight dislocation in a crystal at a point far away from the dislocation core, how does the stress change with the distance r from the dislocation line? So if we draw the stress with respect to distance from dislocation, so it varies like this. Sorry. So this point is generally the uh, having the dislocation orientation at 45 degree, and this is R, and this is the stress sigma. So we have asked that at a point far away from the dislocation core, how does the stress change with the distance r from the dislocation line? So the stress only change to a certain distance from the dislocation core. So it is at origin we have dislocation core, and points far away from the dislocation at both end, this and this, they have constant value of stress. So this straight dislocation in a crystal, the stress at far away point will be constant. Next question would be, so this is the same as previous in we had solved in the same material and under identical condition. The elastic strain energy per unit length of dislocation 1 is twice of dislocation 2. So which of the following can independently satisfy this condition? So we have solved that E1 equals to twice of E2. So V1 will be root 2 of V2. So the C option is correct, and we derived also that first dislocation is edge dislocation and second is the screw dislocation if Poisson's ratio is 0.5. Next question, you asked that for straight dislocation in copper, the Berger vector is 0.25 nanometer, modulus is 48.3. So determine the strain energy per unit length, and the multiplication is 0.5. So the E equals to alpha GB square, if we calculate, so the answer is this 1.5. Next question, while comparing pure edge and uh, pure screw and pure edge dislocation having same Berger vector magnitude, where is the elastic strain energy per unit length and line tension are higher. So we have also solved this question previously. So for edge dislocation, the energy and line tension will be higher. Next question, you asked that in a deformed crystal, the dislocation density rho is 10 raised to power 12 per meter square. So the average spacing d between dislocations is approximately. So the average spacing between dislocation is given by L average equals to 1 by square root of rho. So if we put 10 raised to power 12 meter square, so this will be 1 by 10 raised to power 6 meter inverse. So if we take it, this will be 10 raised to power minus 6 meter. So 10 raised to power minus 6 meter is 1 micron. So the first option is correct. Dislocation spacing will be 1 micron. If we have dislocation density 10 raised to power 12. So moving to the last question, we have asked that when a moving dislocation reaches the free surface of a crystal during plastic deformation, it produces, does it produce fracture, slips, step on surface, grain boundary, phase transformation? So I told that when dislocation reaches free surface, this form this type of step. So the second option is correct. Slip step on surface. So this slip step is generally we cannot see by eyes. So we need very high resolution of SEM to see the slip steps on a crystal. Very high magnification in SEM. Okay. Yeah. So these questions are all for this session. So do you have any other doubt? For the final test, means, will the question be similar or a little harder? The question will be more or less similar, or maybe you can have you will have numericals also. Means for the today session, the topic was general theoretical, so the questions are more of the theoretical. But in the previous lectures, we have big questions in the assignment only. So if you prepare that, so that will be good. I mean, generally उसी type के questions आएंगे. Yeah, you can go to the course page. So in the bottom, one link is given for recorded lectures. Okay, so there can I view live lectures from previous weeks? Yes, you can see. Means the recording is given there. Recording link. Okay, okay, so then we can end to this today's session. Thank you.